another torque question here, just to hammer home the torques. I've got a platform, it looks really scary because I've got this big angle here, but it's not at all. Right, the length of 6 meters, I've got that mass of 4,000 kgs. So 2 meters in the middle here, 3 meters out from the end. That's the wonkiest line I've ever seen. We've got our mass of this beam, 4,000 kgs, is 40,000 newtons, and we've got a thing holding it there which is 2 meters, frictionless pivot point. Well, they've given you the centre of rotation, it's pretty handy, and there's 1,000 kgs, which is 10,000 newton test load, which is right at the end. Which of the following is the closest to the force exerted by the beam downwards on the support? So by this beam downwards on the support. That's going to be equal and opposite from Newton's third law to the force by Mn on KL. So if we can work out what is this force holding the beam up here, what is that force? That's equal and opposite to what the beam is pushing down on the on that support. So that's just what we're going to find out. What's that force there? And we're going to do it through torques, just like we did before. So we set up our torque equation, clockwise equals torque anti-clockwise. What is trying to rotate it down in the clockwise direction? Well, we've got this guy and we've got this guy. He is 3 meters and he is 6 meters. There's no angles, well, apart from the 90 degrees, so we're happy just to write it as FR without the sine theta. Even though you see this thing here, you don't have to worry about it. It's not an angle when it comes to the torques in this actual beam. Because everything compared to the beam is at 90 degrees. Right, the things holding it up, which are counteracting the clockwise, is the anti-clockwise torques, is just this one thing here. Is it holding it up from that pivot point? So FR, just one of them. So we'll just put the numbers in now. So there's 4,000 newtons, my mistake, 40,000 newtons times 3 meters, and 10,000 times from there to there is 6 meters, equals the force we're going to find times 2 meters. So I get 120,000 plus 60,000 equals force times 2. You get 180,000 equals force times 2. I get 90,000 equals force when I solve it. And the last one in this little series is question 9. I've got the same picture there. They want to design it with a reinforcing rods. Okay, so it's concrete. Concrete is weak in tension. The forces, remember, there's a force downwards here, there's a force downwards here, there's going to be a force upwards here. Now, from memory, this force upwards was 90,000, this was 40,000, this was 10,000, so there must be another force here for this to work of 50,000 downwards, 90,000 up. It must be another 40,000 down. Now think of this as a noodle and a pull, like it's a bit bendy. If you're pulling down on this end, pushing up in there and pulling down there, what's going to happen to it? The whole thing, as an exaggeration, is going to end up like this. Now that we've seen how it's sort of bent and stretched, which ends are in tension, which are in compression? Well, this is in tension, and this is in compression, this end, like that. Concrete is weak in tension. This is concrete and it's weak in tension. So it's weak up the top, so it needs to be reinforced up the top. So I don't even have to look at the rest of them. In fact, I didn't even copy them all in, because the answer is obviously A.